Welcome to this coding solution breakdown. Today, we'll tackle LeetCode problem number 998, Maximum Binary Tree 2. This problem challenges us to modify a maximum binary tree efficiently while preserving its properties. Let's dive in and explore how to solve it step by step. In this problem, you are given the root of a maximum binary tree and an integer value, val. A maximum binary tree is a tree where every node's value is greater than any other value in its subtree. To construct this kind of tree, you start by creating the root node with the maximum value from a given array. Then, recursively build the left subtree using the subarray to the left of the maximum value, and the right subtree using the subarray to the right of the maximum value. Now, your task is to insert the given integer val into the tree in such a way that the tree remains a maximum binary tree. The goal is to return the root of this modified tree. The input includes the root of the tree, represented as a tree node object, and the integer val. The output will also be a tree node object representing the root of the updated tree. To better understand, let's look at an example. Consider the input where the tree is represented as 4 1 3 0 2 and val is 5. After inserting 5 into the tree, the output is 5 4 0 1 3 0 2. Here's how the insertion works. Since 5 is greater than the current root value, which is 4, it becomes the new root of the tree. The entire original tree then becomes the left subtree of this new root. This process ensures that the tree remains a maximum binary tree, where the largest value is always at the root. Now let's consider another example. Suppose the input tree is 52401 and val is 3. In this case, the output tree becomes 5240103. Here, 3 is not greater than the root value 5, so it doesn't replace the root. Instead, it gets inserted into the right subtree. Specifically, it becomes a child of the node with value 4, as 3 is less than 5 but greater than 4. This placement ensures the tree remains consistent with the rules of a maximum binary tree. For a third example, let's look at the input tree 52301 with val equal to 6. In this case, the output tree becomes 6502301. Here's what happens. Since 6 is greater than the root value 5, it becomes the new root of the tree. The original tree then shifts entirely to become the left subtree of this new root. This ensures that the tree structure adheres to the definition of a maximum binary tree, where the largest value in the tree always occupies the root position. To maintain the correctness of the solution, it's important to ensure that the tree remains a maximum binary tree after the insertion. Some edge cases to consider include a single node tree, where the insertion might directly replace the root. Another edge case is inserting the smallest possible value, val equals 1, which will always end up deep in the right subtree. Similarly, inserting the largest possible value, val equals 100, will always create a new root. It's also important to test trees of varying depths to ensure the recursive logic handles all scenarios correctly. These considerations will help guarantee that the solution works for all valid inputs. To solve the problem of modifying a maximum binary tree, let's first consider a brute force approach where we rebuild the tree from scratch. The intuition here is straightforward. Treat the tree as an array representation, insert the new value val at the correct position, and then reconstruct the maximum binary tree. This involves 3 main steps. First, perform an in-order traversal of the tree to flatten it into an array. Then, insert val into this array at the appropriate position. Finally, rebuild the tree by repeatedly finding the maximum value in the array and setting it as the root, while dividing the array into left and right subtrees recursively. However, this comes with a significant computational cost. The time complexity is O(n squared), because finding the maximum value during reconstruction is repeated for each level of recursion. Additionally, the space complexity is O(n) due to the extra array. The main drawback of this approach is that it disregards the existing tree structure entirely, even though most of it remains unchanged, making it inefficient for larger inputs. Now, a more efficient solution involves an optimized approach that directly inserts val into the existing tree while maintaining the properties of a maximum binary tree. Here, the key insight is that in a maximum binary tree, the largest value is always the root. If the new value val is larger than the current root, it should become the new root, with the entire existing tree shifted to its left. On the other hand, if val is smaller than the root, it should be placed somewhere in the right subtree. To achieve this, we recursively traverse the right subtree to find the correct position for val. The steps are simple. Compare val with the root value. If val is greater, create a new root node with val, and set the current tree as its left child. Otherwise, proceed to insert val into the right subtree. The time complexity of this approach is O, h, where h is the height of the tree. In the worst case, for an unbalanced tree, this could be O, n. The space complexity is also O, h, due to the recursion stack. By avoiding unnecessary reconstruction, this approach ensures efficiency. This optimized approach offers several key benefits. First, it modifies the tree in place, which makes it significantly more efficient compared to starting over with a full reconstruction. Second, it avoids redundant computations by leveraging the existing tree structure. As a result, it is particularly well suited for large trees, where the brute force approach would be prohibitively slow. After comparing both methods, we've chosen the optimized approach, also known as direct tree insertion, as our preferred solution. It balances efficiency and simplicity effectively. The recursive insertion process ensures that the maximum binary tree properties are preserved while minimizing computational overhead. Let's also consider some trade-offs. In terms of efficiency, this approach is much faster, operating in O, h, time for tree height, compared to the O, n squared, complexity of the brute force method. It is also simpler to implement, as it doesn't require extra steps like flattening the tree into an array. Finally, this approach naturally handles edge cases, such as inserting into an empty tree or when val is the largest or smallest element, making it robust and versatile. In summary, the optimized approach strikes the right balance between performance and simplicity, making it the ideal solution for modifying a maximum binary tree. By directly inserting the new value into the tree, we maintain the tree's properties while avoiding the inefficiencies of a full reconstruction. This method is both efficient and elegant, ensuring that the solution scales well even for larger inputs. With its ability to handle edge cases seamlessly and its minimal computational overhead, the optimized approach is well suited for this problem and provides a clear path to the desired result. To understand how to solve this problem, let's first revisit the concept of a maximum binary tree. In this structure, the root is always the maximum value from the array used to construct it. The left subtree results from the maximum binary tree built using the elements to the left of the root in the array, while the right subtree is constructed using the elements on the right. Now, the challenge is to insert a new value into such a tree while maintaining these properties. One straightforward approach to solve this is to rebuild the tree entirely, starting from the array representation. The first step in this brute force method is to recover the original array that was used to construct the tree. This is possible because a maximum binary tree can always be uniquely mapped back to its original array. To achieve this, we can perform an inner traversal of the tree. During this traversal, the root, which is the maximum of its subarray, along with its left and right subtrees, aligns perfectly with the structure of the original array. This gives us the foundation we need to proceed with the solution. After recovering the original array representation of the tree, the next step is to insert the new value, as the problem specifies. To do this, we simply append the new value to the end of the array. By appending, we ensure that the relative order of elements in the array is preserved, which is crucial for maintaining the properties of the maximum binary tree. Once the new value is added, the next step is to reconstruct the maximum binary tree from this updated array. The process of rebuilding the tree involves three key steps. First, we identify the maximum element in the current subarray, which will serve as the root of the subtree. Next, we divide the array into two parts. Elements to the left of the maximum value will form the left subtree, while elements to the right will form the right subtree. Finally, we recursively apply this process to construct both the left and right subtrees. Rebuilding the tree in this way ensures that the new structure adheres to the rules of the maximum binary tree. However, it's important to note that this brute force approach is computationally expensive, as finding the maximum element in each recursive step requires linear time, leading to an overall time complexity of O, n squared. There are also a few edge cases to consider when implementing this algorithm. If the tree is initially empty, the new value simply becomes the root. If the inserted value is greater than any existing value in the tree, it becomes the new root, and the entire tree shifts to its left. On the other hand, if the inserted value is smaller than all existing values, it will be placed in the rightmost chain of the tree. To implement these steps programmatically, we use two primary data structures: an array to temporarily store the tree's array representation during reconstruction, and a tree node class to represent the nodes of the tree. The final algorithm can be broken down into three main steps. First, we extract the array representation of the tree using an inner traversal. Next, we append the new value to the array. Finally, we rebuild the maximum binary tree using a recursive approach. In the pseudocode, we define a function that constructs the tree by finding the maximum value in the current subarray, setting it as the root, and recursively building the left and right subtrees using the partitions of the array. These steps ensure correctness while maintaining the properties of the maximum binary tree. To complete the reconstruction, the recursive function returns the newly built tree, which serves as the updated root of the maximum binary tree. While this brute force approach works, there are opportunities for optimization. Instead of rebuilding the entire tree, we can explore in-place adjustments that leverage the structural properties of the maximum binary tree. Such advanced approaches can significantly reduce the computational overhead. In terms of space complexity, the current algorithm uses O(n) space for storing the array representation and another O(n) space for the recursion stack, resulting in a total space complexity of O(n). Optimizing this algorithm, particularly by minimizing redundant operations, can help improve both time and space efficiency, making it more suitable for larger input sizes. This implementation solves the problem of inserting a new value into a maximum binary tree while maintaining its properties. The tree-node class defines the structure of a binary tree node with attributes for the node's value and its left and right children. This is a standard implementation for representing binary trees in Python. The insertIntoMaxTree function in the solution class is the core of the solution. It takes the root of the current maximum binary tree and the value to be inserted as inputs. The algorithm follows these steps. 1. Base case in new root creation. If the tree is empty or the new value is greater than the value of the root node, a new root node is created with the new value. The current tree becomes the left child of this new root. This maintains the property that the root is the maximum value in the tree. 2. Recursive insertion into right subtree. If the new value is less than or equal to the current root's value, we recursively call insertIntoMaxTree on the right subtree. This ensures the new value is placed in the correct position while maintaining the tree structure. 3. Return updated root. After the insertion, the updated root is returned, propagating the changes back up the recursion stack. This approach efficiently handles the insertion by leveraging the properties of the maximum binary tree, ensuring the solution is both correct and optimized. The algorithm runs in O(h) time, where h is the height of the tree, as it only traverses down one side of the tree. This is the Java implementation of LeetCode problem number 998, Maximum Binary Tree 2. The logic mirrors the Python implementation provided, with key differences such as explicit type declarations, Java's class structure, and the absence of default parameters in constructors. The insertIntoMaxTree method recursively inserts a value into the maximum binary tree, maintaining its properties. If the new value is greater than the root, it becomes the new root, with the previous tree as its left child. Otherwise, the method traverses the right subtree. To solve LeetCode number 998, Maximum Binary Tree 2, we need to understand the properties of a maximum binary tree. The root of this tree is always the maximum value, and all values in the left and right subtrees are smaller than the root. When inserting a new value, the goal is to maintain these properties while returning the updated tree. For example, if the input tree is empty, as shown here, we simply create a new node with the given value. Since there is no existing structure, this new node automatically becomes the root, completing the insertion process. The resulting tree from the previous step consists of just the single node with value 5, which is both the root and the only element in the tree. Now, consider a scenario where the new value to insert is greater than the current root. For instance, if the tree starts with 3 as the root and contains a right-skewed structure of values 3, 2, and 1, and we are tasked with inserting the value 4, the process will differ slightly. Here, the root value is 3, and the new value to insert, 4, is greater than the root. According to the rules of a maximum binary tree, the new value becomes the new root. To achieve this, we create a new node with value 4 and assign the entire existing tree, starting from the original root of 3, as the left child of the new root. This ensures that all values in the left subtree remain smaller than the new root. The resulting tree now starts with 4 at the root, with the original tree structure shifted to its left. Now, let's look at a case where the new value is smaller than the current root. For instance, if the tree starts with 5 as the root and contains a left-skewed structure of 5, 3, and 2, and we are tasked with inserting the value 1, the process involves traversing the right subtree. Since the new value, 1, is less than the root value, 5, we move to the right child. Here, the right child is empty, so we create a new node with value 1 and assign it as the right child of the root. The left subtree remains unchanged. After inserting the new value, the updated tree maintains the maximum binary tree properties. The root remains 5, with the left subtree still containing 3 and 2, and the new value, 1, is placed as the right child of the root. This placement ensures that all values in the right subtree are smaller than the root. From these examples, we can derive key observations. If the new value is greater than the root, it becomes the new root, and the existing tree shifts to its left. If the new value is smaller, we traverse the right subtree recursively until we find an empty spot for the new node. Lastly, let's consider the time and space complexity of this approach. In the best-case scenario, when the new value becomes the root, the insertion takes constant time, O1. In the worst case, where we need to traverse the deepest right subtree to find the insertion point, the time complexity becomes O(h), where h is the height of the tree. Similarly, the space complexity is O(h), due to the recursive calls made during the insertion process. This completes our analysis of the problem. When analyzing the time complexity of the insert into maxtree function, we start with the best-case scenario. In this case, if the new value val is greater than the root node's value, a new root node is created with val as its value, and the entire existing tree is attached as the left child. This process doesn't require any traversal of the tree, so the time complexity is constant, or O1. On the other hand, in the worst-case scenario, the new value val is smaller than all the values in the tree. Here, the function must traverse down to the rightmost node in the tree. For a tree with n nodes, if the tree is skewed so that all nodes are aligned in a single branch, the traversal would involve visiting all n nodes. As a result, the time complexity in this case is O(n). Now, let's consider the average case for time complexity. In a balanced binary tree, the depth of the tree is approximately proportional to log n. Finding the correct position for the new value in the right subtree would therefore require about O log n time on average. Summarizing all cases, the time complexity of the insert into maxtree function is O1 in the best case, O log n in the average case, and O(n) in the worst case. Shifting to space complexity, this is determined by the memory used for the recursion stack. In the best case, when the new value becomes the root, no recursion occurs, so the space complexity is O1. In the worst case, where the tree is skewed, the recursion stack grows with the depth of the tree, leading to a space complexity of O(n). For the average case in space complexity, a balanced binary tree has a height proportional to log n. This means the depth of the recursion stack will be approximately log n, resulting in a space complexity of O log n on average. To summarize the overall space complexity, we have O1 in the best case, O log n in the average case, and O(n) in the worst case. Comparing this solution to a naive approach helps illustrate its efficiency. A naive method might involve reconstructing the entire tree from scratch after inserting the value, which would require traversing all nodes and rebuilding the tree. This brute force method would result in both time and space complexities of O(n). In contrast, the optimized approach modifies the tree in place, focusing only on the rightmost path where the insertion is needed. This minimizes unnecessary operations and achieves optimal time and space complexities across various scenarios. In summary, this solution is optimal because it avoids reconstructing the tree entirely. Instead, it directly inserts the new value in the correct position with minimal traversal. The time complexity ranges from O1 in the best case, where no traversal is required, to O(n) in the worst case, where the tree is skewed and every node must be visited. Similarly, the space complexity depends on the recursion stack depth, ranging from O(1) in the best case to O(n) in the worst case. By modifying the tree in place and limiting unnecessary operations, this approach achieves significant efficiency both in terms of time and space. When working on problems like maximum binary tree 2, there are a few common mistakes to watch out for. First, reconstructing the tree incorrectly can happen if you fail to preserve the maximum binary tree properties. Remember, the root must always be the maximum value in the array, and violating this structure creates an invalid tree that doesn't meet the problem's requirements. Another mistake is not maintaining the mapping between array elements and tree nodes. If you fail to track this properly, you might end up performing redundant computations, which can lead to unnecessary complexity. For example, instead of achieving an O(n) solution, your approach might degrade to O(n)² in performance. Lastly, overcomplicating edge cases is a mistake too. Situations like inserting at the beginning or the end of the tree can be handled naturally within a generalized approach. Adding unnecessary checks often leads to harder to maintain code and increases the likelihood of introducing errors. Simplifying your logic where possible is key to writing robust solutions. Another mistake to avoid is ignoring opportunities for in-place optimization. Using excessive additional data structures, like repeatedly copying subarrays, can significantly increase memory usage and runtime. This is especially problematic for larger inputs where efficiency is critical. You should aim to reduce unnecessary overhead wherever possible in your implementation. Additionally, misunderstanding input constraints is a common pitfall. For instance, assuming the tree must always be balanced or making other unsupported assumptions about the input can lead to solutions that fail for valid edge cases. It's important to carefully read the problem description and design your solution to generalize well across all possible inputs. Misinterpreting constraints can be avoided by taking a systematic approach to understanding the problem requirements upfront. In interviews, it's essential to demonstrate a clear understanding of the maximum binary tree properties. Be ready to explain how the tree is constructed. The root is always the maximum value, and the left and right subtrees are formed based on the array partitions. Efficiently handling insert operations is another key point. Instead of rebuilding the entire tree, think about how to preserve the tree structure as you insert new elements. This not only highlights your optimization skills but also showcases your ability to work within constraints. Always communicate the trade-offs between different approaches. For example, discuss the pros and cons of a brute force solution versus an optimized one, especially in terms of time and space complexity. Finally, be prepared to address edge cases, such as inserting at the beginning or the end of the array, handling duplicate values, or working with very large input sizes. These details show thoroughness in your thought process. It's also helpful to explore related problems and alternative approaches. For instance, LeetCode 654 focuses on constructing the maximum binary tree, which is the foundation for this problem. LeetCode 105 and 889, on the other hand, deal with constructing binary trees from pre-order and inorder or post-order traversals, which can deepen your understanding of tree construction techniques. Now, when it comes to alternative approaches, one option is brute force reconstruction. This involves rebuilding the entire tree for every insertion. While simple to implement, this approach is highly inefficient for larger inputs, with a worst-case complexity of O(n)². A more efficient option is iterative tree modification. This involves traversing the tree to find the correct position for the new node without rebuilding the entire structure. While this approach is faster, with O(n) complexity, it requires careful handling of pointers, which can increase the implementation complexity slightly. Another powerful approach is optimized recursion. Here, you use a recursive function to modify the tree directly while maintaining the maximum binary tree properties. This method can result in cleaner and more elegant code, as recursion naturally aligns with the hierarchical structure of trees. However, it's important to consider potential limitations, such as stack overflow for very deep recursion. This is especially relevant for extremely large input sizes, where the recursion depth can become a bottleneck depending on the constraints of the programming environment. Balancing the simplicity of recursive solutions with their potential downsides is an important consideration when designing your approach. By understanding these trade-offs and selecting the most appropriate method for the scenario, you can create a solution that is both efficient and robust. Great job making it to the end. To summarize, we covered the key steps to modify a maximum binary tree and analyzed the trade-offs of our approaches. Remember to practice similar problems to strengthen your skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!